The topic of the video is space displacement unitary operator. If the ket psi r is a state vector of a system at location r, an operator which you can call t hat dr can actually operate on this ket vector to transform it to another ket vector which is psi at r plus dr. That means mathematically you can write that as equation number Roman I, and such operator T dr is called space displacement operator. Properties of these space displacement operators. The first one is if the length of ket psi r is 1 and also the length of ket psi r plus dr is also 1, then since this first equation implies that the length of bracket of psi r plus dr can be written like this, so it should be equal to only the bracket of ket psi r and psi r, bracket of psi r and psi r, only if t dagger is equals to t inverse. That means t is a unitary operator. So this property, this first property is actually saying a kind of a proof for the operator t being a unitary operator. And then the second property is that if you have taken two time displacement operators as t dr1 and t dr2, and then if you take their product which is t dr1 into t dr2, then it should be equal to t at dr1 plus dr2. And number 3 is that in the limit of dr going to small number, that is 0, then t dr will tend to identity operator I, and so we can write that t0 is actually kind of identity operator. And number 4 is that if you actually have t minus dr, then it's also equal to t inverse of dr. That's because if you take the product of t dr and then t minus dr, which should be giving t of dr minus dr, which is t of 0, and from number 3, property number 3, t0 is equal to identity operator I. Therefore your t minus dr is equals to t inverse of dr. And the property number 5 is that if you take a product of t dr1 and then t dr2, and if you take the product in reverse way also, which is tdr2 and tdr1, the result will be same. So here we can say the property number 2 as the closure property, and property number 3 is identity property, and then number 4 as inverse property, and number 5 as the commutativity property. So we can say that the set of all space displacement operators satisfy the properties of abelian group under multiplication. The expression for space displacement operator. The Taylor series for a function psi of x around a point A can be written as this summation. And if you neglect the second order terms and above, you get psi x like this. Here we are doing a trick, kind of a cheating actually on the right hand side in the first term, that dou by dou x should be done first, and then a should be substituted in place of x later on, but we are straight away writing psi of a here. It's actually cheating, but it helps in finding out an expression for the operator t in easier way. So if a is very near to your x in right hand side, we can actually write down x plus dx in place of a. And if you do that, the psi of x can be written as psi of x plus dx, and then the second term as shown here. And on the right hand side, if you pull out psi of x plus dx, then we get the thing in the square bracket in front of it. But the expression for momentum operator px was in terms of dou by dou x. So we can write dou by dou x is equals to ipx divided by h cut. So our psi can be written in terms of the operator p like this. And if we actually multiply with the inverse of the operator, which is in the square bracket on both sides, we can actually get expression for psi of x plus dx like this. Since it is since the operator in square bracket is unitary, we can actually take u inverse as its dagger also, which gives us that the psi of x plus dx is equals to I plus dx I by h cut into px into psi of x. Therefore we can write the space displacement operator t dx as I plus dx I by h cut into px. Similarly, the space displacement operators along y direction and z direction can be written as shown here, where in place of dx will be having dy, and in place of dx will be having dz in the second case. So and here we say px, py and pz as the generators of space displacement along x, y and z directions. That's it in this video. Thanks for watching.